In this session, the International Association of Engineers Distinguished Scientist Award, Data Mining and Machine Learning Presentation Ceremony. Our laureate of the award is Professor Geoffrey McLachlan. His distinguished science speech is an apparent paradox in machine learning. Semi-supervised learning can typically produce more accurate classifier than full supervision. And in this session, our association had arranged 3 session co-chairs to represent our association. And the Professor Palat will be the first session chair to make the introduction, then followed by Professor and I will conclude the introduction, and then Professor McLachlan, then you can speak your distinguished science speech. So without further ado, first, Professor Palat.
Okay, thank you very much for the invitation and for having this opportunity to introduce Professor Geoffrey McLachlan. I hope I can pronounce it correctly. Professor Geoffrey McLachlan is a professor of statistics and personal chair in the School of Mathematics and Physics, University of Queensland, Australia. Professor McLachlan obtained his BSc in mathematics at the University of Queensland in 1969. He went to pursue then a PhD at the same university under the supervision of Stephen Lipton, a former staff member at the famous Rothamsted experimental station in the UK. Professor McLachlan received his PhD from the University of Queensland in 1974 and his DSc from there in 1994. He has served in many positions of academic service over his career, most notably including as an Australian Research Council College of Experts member between 2008 and 2010. Professor McLachlan is world-renowned in the fields of computational statistics, pattern recognition, machine learning, and neural network, and he has written over 300 research articles. Google Scholar lists Professor McLachlan with an H index of 63 and attributes over 60,000 citations to his publications. Professor McLachlan serves on the editorial boards of several journals like Advances in Data Analytics and Classification, BMC Bioinformatics, Cancer Informatics, Journal of Classification, Statistics and Computing, Statistical Modeling, Statistics Survey, and Wires Data Mining and Knowledge Discovery. Professor McLachlan has also supervised numerous PhD students over his career. The themes in McLachlan's work include the use of finite mixtures of atypical distributions for clustering of complex data. And I will give the next speaker can continue.
Yeah, Professor, yeah, you can continue.
Okay, you can hear me, right?
Yes.
Okay, now, dear colleagues and esteemed guests, this is Carl from Asia University from Taiwan. It's certainly with my great pleasure, and I present to you the laureate of the Distinguished Scientist Award in the area of data mining and machine learning, Professor Geoffrey McLachlan. I hope I pronounced your last name correct.
Yeah, that's right. Yeah.
Yes, Professor Geoffrey McLachlan. Exceptional contributions and groundbreaking research have been recognized and celebrated by prestigious institutions and fellow experts in the field. So join with me in acknowledging his remarkable achievements and the impact he has made in advancing our understanding of his respective field. The honors and awards won by Professor McLachlan include the following: Australian Research Council Professional Fellow, Pitman Medal of the Statistical Society of Australia in the year of 2010, ISI High Cited Author 2010, He's the president of the International Federation of Classification Society from 2010 to 2011. His the IEEE ICDM Research Contributions Award in 2011. The University of Queensland Vice Chancellor Senior Research Fellow, 2012 to 2015. Shell Shirley, a visiting fellow at Victoria University of Wellington, New Zealand at 2014. He's the fellow of the Australian Academy of Science 2015, the research medal of the International Federation of Classification Societies. So without any additional delay, I will now hand over my microphone to Dr. Sunny Oh.
Thanks, Professor Palat and Professor Ng. And as said, the focus of our session is on the award presentation and also on the video recording, so that it will become a open access Distinguished Scientist Award speech series. And then after the video production, we will send the video to our ordinary members so that they can, enjoy the video. This is our objective, so that they do not need to travel, and also they do not need to pay any registration fee for the conference in order to have the keynote speech session. And before the COVID, usually we hold the meeting physically, and we can make the award presentation physically. But now we can only make this virtually award to Professor Geoffrey McLachlan now. Yeah, this is your award. And for the physical award and physical trophy, when we have co-chair that will come to, who will go to Australia, then we will arrange him or her to present the physical award certificate and also award trophy to you in person. Yes. And without further delay, so let's make a big hand to Professor Geoffrey McLachlan for his speech.
Well,
Yeah.
thank you.
Yeah.
Thank you.
Yes,
Thank you very much.
great honor.
Sonny, I'm humbled, very humbled to receive this award, but also I'm very delighted too. So, okay. Well, so my talk today is on this apparent paradox, which I find very surprising. So so this is on a recent result with Daniel Arfock, and it's the fact that a classifier based on a partially classified, I'm using the word classified in the same sense as being labeled, but so it says that a classifier based on a partially classified sample can actually have smaller expected error rate than if the sample were completely classified. So we found this a very surprising result. Now, clearly, this result needs some assumptions to hold for it to be valid. And firstly, we adopt a generative model approach where the joint distribution of the observations and their labels is assumed known up to a vector theta of unknown parameters. And secondly, it's postulated that the probability the feature data have missing labels depends solely on their entropy. This is a key assumption. And this assumption here applies to situations where the unlabeled entities tend to fall in regions of the feature space in which classification is difficult to perform, such as regions near the class boundaries, which have high entropy. Now, a fundamental issue in semi-supervised learning, which I'll call SSL now, is identifying the mechanism responsible for the unlabeled feature data. And indeed, one could say that SSL is not really intended to be used without any prior assumption about the distribution of the missing labels. And there's also the question of whether the use of unlabeled data can hurt the learner. But in our case, we're using a generative model approach. And so assuming that the model is correct, well then the adding unlabeled data will not hurt the classifier. Now, before I get on to the result, just a few general remarks about semi-supervised learning. Now, I think we all know that deep learning achieves excellent performance in supervised learning where labeled data are plentiful. And I've put down this reference to LeCun, Bengio, and Hinton, because regarded now perhaps as the three godfathers of artificial intelligence. However, labeling large amounts of data is often prohibitive due to time, financial, and expertise constraints. Now, the goal of semi-supervised learning is to leverage large amounts of unlabeled data to improve the performance of supervised learning over small data sets. And so recently, there's been increasing interest in applications using semi-supervised learning in the machine learning community, spurred on by its impressive empirical progress and on benchmark image and text classification data sets. And many proposals have been put forward, and there's a book by Chappell devoted to semi-supervised learning. Now, there's many methods being put forward for semi-supervised learning, and they typically involve one or more of these assumptions. I won't go through these assumptions in detail here, but they're not distinct from each other. There is some overlap between them. And indeed, in our generative model approach, these sort of assumptions are implicit in the model. So, okay, well, that's enough about semi-supervised learning. What I want to now is to define the problem that I'm talking about. So I'm dealing with classification, which is a very common task in machine learning. And so we want to consider the formation of a decision rule, or I'll call it a classifier, which I'll denote by capital RY, to assign an entity to one of G predefined classes, which I'll denote by C sub 1 to C sub G, on the basis of some observed data Y, which I'll call the feature vector. And so this rule takes the value I. If it does take the value I, it implies the entity is assigned to the ith class. So we've got the learning now of the classifier. So we've got the training data consists of these observed feature vectors, Y sub 1 through to Y sub n. And associated with them are their class labels, Z sub 1 through to Z sub n, or I suppose in America they would say Z sub 1 to Z sub n. So these Zs, they're the labels. And you can think of them as either being scalars, that is, they take the value 1, 2, up to G, depending on whether the feature vector comes from the particular class, or I'm thinking of these as G-dimensional vectors, and they've got zeros everywhere except in one position. So if they've got a 1 in the third position, it's implying the feature vector comes from the third class. Or if they've got 1 in the fifth, it comes from the fifth class. Now, for the particular problem that we're trying to prove that we can do better than supervised learning with semi-supervised learning, we've got these missing label indicators, M sub 1 through to M sub n. So this indicator, M sub 1, is 1 if Z1 is unavailable. That is, Y1 is an unclassified observation. And it's equal to 0 if Z1 is available. That is, Y1 is a classified observation. So we've got supervised learning where all the MJs are 0. That is, all the observations are labelled in the sample. And we've got unsupervised learning where all the MJs are 1. That is, all the labels are missing. And we've got the case in between there called semi-supervised learning where some of the MJs are 1. That means we've got some feature data with missing labels. So we're going to adopt a generative model approach where the joint distribution of Y and Z corresponding to the realization of the feature vector Y and its label Z is assumed known up to a vector of unknown parameters theta. And the conditional density, since we know the joint distribution of Y and Z, the conditional density of Y, given that it comes from the ith class, we know that, and we'll denote it by F sub I. And it depends on a parameter vector omega sub I. And this pi sub I, we're going to let be the prior probability that the observation belongs to the ith class. So as I said, this Z is a vector, and if the ith element in this vector is 1, it implies that Y comes from the ith class. Now the density of Y is given by this G component mixture model. So that's a bit of notation out of the way. We don't have to try and recall this notation as we go, but so this is the optimal or Bayes rule. And now the rule depends on Y, and it also depends, well, this is a rule for the allocating the feature vector Y, and it depends on theta. And it assigns an entity with feature vector Y to class CK if it assigns it to class CK if the posterior probability that Y belongs to this class CK is greatest for K. That is, K is the argmax I of the posterior probability. So this posterior probability is the probability that the entity with feature vector Y belongs to the ith class. And so using Bayes' theorem, it's given by pi sub I, F sub I over the density of Y. So before we actually view Y, we've got a prior probability pi sub I that it comes from the ith class, but then having viewed Y, that probability we work with now is the posterior probability. And the class to which this posterior probability is greatest is the class to which we assign the entity with feature vector Y to it. So I'm not too sure if you can see the top line, but if you can see the top line, but it but it's saying that we've got a partially classified sample Y sub 1. Well, this is a transpose sign here. I'm writing everything as a vector. We've got a partially classified sample Y sub 1, Z sub 1 through to Y sub n, Z plus n, where the feature vectors Y sub j are all observed, but some of their class labels Z sub j are missing. Now, we consider the estimation of Bayes' rule in the framework of Don Rubin, 1976, for missing data, where the missing indicator variables, M sub j, are treated as random variables. So we're treating these missing label indicators, M sub j, as a realization of random variables. Now, Rubin didn't work on semi-supervised learning. He put forward this framework in a general context where there's missing data. And this missing data mechanism is in terms of the conditional distribution of these missing label indicators given all the observed data. So to summarize that last slide, we're putting forward a framework for the missingness of the labels of the unclassified features. And we're going to treat these labels of the unclassified features as missing data and then introduce the framework put forward by Rubin. And on introducing these random variables corresponding to the realizations, we specify their distribution conditional on all the observed data. So this is our underlying framework for trying to make use of the missingness in the labels that are not available. Now, this is the way that Rubin defined the missingness. So MCAR is missing completely at random, and it says the probability that MJ is 1, that is the probability that the label associated with Y sub j, the probability that this label, which for Y sub j is 1, that is it's missing, conditional on Y sub j and Z sub j, doesn't depend on Y or Z. It's just a constant. It may depend on some parameter, which I've called xi, but this xi is distinct from theta. So that's missing completely at random. And then we've got missing at random, where this probability now can depend on Y sub j and theta. And this is important because it depends on theta, and we're trying to estimate theta. So if we can bring this term into the likelihood, it'll give us the opportunity to find more information about theta. And missing not at random is where this probability that a label is missing depends, given yj and z sub j, depends on y sub j, z sub j. This is missing not at random, and we're not interested in this particular case. This is a case where we're going to be working with. But firstly, I want to look at the first missing completely at random. So, I didn't miss out saying something. Now, if the probability that MJ is 1, given Y sub j and Z sub j, doesn't depend on theta here, it's just got Y, it only depends on Y sub j and that. This is called ignorable missing at random. We can forget about this. It's not going to, we can just go ahead and use the likelihood regardless of this, because it doesn't come into the likelihood. There's not going to be any extra information provided by it. And it's called non-ignorable if there's a theta here. And that's the case we want to focus on. But firstly, a model for ignorable missing at random labels is, as we said, the probability of MJ being 1, given Y sub j and Z sub j, is just a function of Y sub j. And it may depend on some parameter xi, which is distinct from theta. And under this model, the missing label mechanism can be ignored in forming the likelihood function for theta. And okay, so we want to form that likelihood. So we've got this term here now, log of L subscript C of theta. So we go ahead and form the likelihood by summing over the log of the density of the Z sub j and the Y sub j. And we pick out the classified ones, because if MJ is 0, if the observation is classified, so it gets included. Whereas if it's not, MJ is 1 and it doesn't get included. And now we've got the corresponding term for the unclassified data, where for the unclassified data, we've just got the Y's. So the likelihood, the log likelihood, is obtained simply by summing over the log of the density of the Y's. Now, then the likelihood that we can form from the classified and unclassified features is given by here. Now I'm calling this now the log likelihood based on the partially classified sample, and the IG stands for ignore. That is, we're ignoring the fact that the labels are missing at random. We're making use of that, which says we can ignore it. So this is the likelihood function that we use, and we're not going to gain any information from the missing label mechanism. Now, there's very few results around for semi-supervised learning, but we're adopting a generative model approach, and that gives us an opportunity enables us to derive some results that are mathematically tractable. And so we're going to suppose that the feature vector's got a normal distribution, but with a common covariance matrix in each of two classes. And in this particular case, the Bayes rule, the Bayes classifier, is just a linear function of y. And so we've got a parameter vector, theta, of all the parameters, but when it comes to estimating the Bayes rule, we just need to focus on beta. And so here's the total parameter theta, and we decompose it into beta, and then we've got some other parameters we're not interested in. And we've got this delta. This delta is the Mahalanobis, well, this is delta squared here, but the square root of it is the Mahalanobis distance between the two classes. So in the case of two classes where they're normal with a common covariance matrix, there's a very convenient parameterization. Now, so where do we go from here? I don't think I can move this. I can't move, oops, I can't move this down. The top, oh. I seem to, yeah, there's a top line here. Unfortunately, it looks like this line here, except that it's got beta hat CC. So, okay, briefly, this notation, I'm trying to define the asymptotic relative efficiency of this rule. So this is just some rule that's estimating the Bayes rule, and it's based on this partially classified sample. And so on the denominator, we've got what I call this a conditional error rate when we use the rule, this rule here. And it's a function of the true value of beta and the value of this estimate. And when we replace this estimate by the true value of beta, then we get the optimal error rate here. And then on the denominator, we've got the same thing, except instead of having the estimated rule for the partially classified, estimated parameter for the partially classified sample, we've got the estimate of beta using the completely classified sample. And this difference, when we take this expectation of these terms, they're both equal to this. This is the optimal error. So this difference here is what's called the excess error. This is the extra error that you get by not knowing the true value of beta and having to estimate it. And we can do a Taylor series expansion of this, and we end up getting it in terms of this ratio here. Now, this term ACCB, it's n times the inverse of the information matrix for the completely classified sample, the information about beta. And AUC is the information or the inverse of the information about the completely unclassified, about the sample when it's completely unclassified, the information about beta, and we've got an n there. And then this term, this matrix here, is just the matrix of second order partial derivatives, because we do our expansion. So these terms here are really the coefficient of 1 on n in our expansion of this, of each of these errors. And so we can get results out for the asymptotic relative efficiency if we can work out these this information matrix. So we've got to be able to work out these information matrices. Now, for generative classifiers constructed by modeling the joint distribution of the features and the labels, it's possible to compute this Fisher information in the unclassified observations. So the benefits of using unlabeled data can be assessed on a theoretical basis. If I go back here, this is the Fisher information matrix. And it plays a key role in looking at the relative efficiency of these rules. So how do we get this Fisher information in this case? Well, we've got the joint density of y and z. It's the density of y times the conditional probability, really, of z given y. And in the case where we've got normal densities, in the classes. This LR stands for logistic regression. This is the logistic regression form for the probability. So we can now go ahead and form our likelihoods for a completely classified sample. It comes out to be the likelihood when the sample is completely unclassified, and then we've got the log of the likelihood for logistic regression. And so when we differentiate these terms twice, because the Fisher information is the expected value of the negative of the Hessian of the likelihood function. So when we do that, we get that the information about beta in a completely classified sample is the information about beta when it's completely unclassified, plus the conditional information about beta in the using logistic regression on the completely classified sample. And so the information about beta in a partially classified sample comes out to be the information in the completely classified sample less m bar, that's the proportion of observations that are unclassified, times this information here. So by using a partially classified sample and not a completely classified sample, we lose this information here. Now, trying to work out the information in the logistic model for beta is proved a bit of a, I'd say, a stumbling block. But in 1975, Brad Efron was able to derive an expression for it. And so then his PhD student, O'Neill, was able to derive the asymptotic relative efficiency. And I put this up here in this table. This is in the case of where you got a single variable, p equals 1. Although in the case where the prior probabilities are equal, it's true for all values of p. But you can see that if delta is 2, the Mahalanobis distance is 2 between the two classes, that is the optimal error rate's about 0.1587. So the ARE is 10. So these are percentages. So if you invert this, it means if you're going to use an unclassified sample, it has to be 10 times larger than the classified one to get the same error rate. This is if you got completely unclassified. And here, if delta's 3, the classes are getting far apart now. You need about 3 times the sample. So anyway, that was the result using a model that you can ignore the missingness. And an example where you can ignore the missingness is, say, here, where you've got a measurement, it's a scalar, and if it's greater than k, then you actually can define the work out the label. It may be a person has very high blood pressure, then the doctor may consider that it's sufficiently important to perform some tests to work out whether the person has this particular condition or not. And if it's less than k, the observation is left unclassified. And we can work out what the ARE will be. So when k is infinity, that is the sample is completely unclassified, and this is what we had before. But as we reduce k down, we get more classified observations, and the ARE will increase. So coming back to this result here, coming back to this result here, this efficiency is 10. If we were to take half the sample to be classified and half to be unclassified, then this would drop to about 0.5 to 5. So it would drop to 5, the percentage 5. So we'd only need twice as large a sample to do as well. So that's why having so there's not much information in an unclassified observation, but if we get a lot of them, then they can help. Now we're coming back to what's in the result I'm trying to really prove. We've got a model now where we can't ignore the missing at random labels, and so we're letting Q y sub j theta xi be the probability that a label is missing given the value of the feature vector and Z. Well, we take it not to depend on Z because otherwise it wouldn't be missing at random. So now what the, I must admit it was my co-author who thought about this idea. He said, let's take this to be a function. This is a probability. Let's take it to be a function of the entropy. So here's the entropy of an observation. It's just minus the sum of a posterior probability times the log of it. So he said, let's take it to depend on the entropy. And normally, and if you're trying to model a probability versus against a covariate, we use it's inobvious that we should use the logistic regression. And rather than use the entropy here, we use the log of the entropy. So we took the minus. Now, so why did we do that? Well, we wanted to help in the case of G equals 2, normal homostochastic classes, the log of the entropy can be written like this. It's a function of the square of the Bayes classifier. And it's easier to differentiate this than to differentiate this in working out the results. So that's why we wrote that. That's why we wrote this as minus log rather than plus log. So now, with non-ignorable missing at random labels, the full likelihood for theta and xi now is given by the log likelihood where we ignores the missingness mechanism. And now we've got this term here because this is the log of the probability of getting the labels M sub j, and it's just a binomial probability. But we've now got an extra term here, and so this is going to increase the information we can get from that sample. So with the Bayes classifier now, the amount of information about beta, using what I call the full likelihood, this is the full likelihood, it's the so the information about beta using the full likelihood for a partially classified sample is the information in the completely classified sample. Then we get this term, which we saw that we lose. It's minus gamma, the proportion of unlabeled observations in the sample, times the information about beta in a completely classified sample using logistic regression. But now we gain the information about beta where we using the missingness of the labels. So this is gamma. It's just the proportion of unlabeled observations, and this is a theorem I've taken it from the paper, but it's just that we've got this expression now where we take the information about theta for the full model, and then having got that, we're able to pull out the information about beta, because we're really interested in beta here, not theta, the whole parameter, the parameter vector of all the parameters, the vector containing all the parameters. Now, looking back on this, if this term here is greater than that, it means that we've overcome the loss of these observations being unclassified because they provide this information. So if the information about beta in the likelihood based on the missing labels, the distribution of the missing labels is greater than gamma times the information about beta in the logistic regression based on the completely classified sample, then this means there's more information. And so this inequality holds for various combination of the parameters, which implies that the estimate of beta now, using the partially classified sample, is more efficient than the estimate of beta based on the completely classified sample. And a consequence of this is in such situations, the asymptotic expected error rate of the estimated Bayes rule is actually smaller than that of the rule based on a completely classified sample. And so we've worked out the asymptotic relative efficiency of this full rule relative to the rule. It's a full rule, but it's based on the partially classified sample, compared to the rule where it's based on the completely classified sample. Now, when we defined it, we put the excess error rate for the completely classified, for the classifier based on a completely classified sample on the numerator, and put the excess error for the Bayes rule based on the partially classified sample, because we thought it would be greater. But as you can see here, these aren't percentages anymore. These are actual ratios. You can see most of these values are greater than 1, meaning that this rule here is doing better than the rule based on a completely classified sample. And for example, where the probability of a missing label depends heavily on the entropy, we get, that is xi1 is -10, say, we get a value of 40. So we get some very large values, which really surprised us. Oh, now you can't see, this is too small really, but anyway, you can see a value here. We did some simulations. We took n equals 500 and we took p equals 1 here, and this, we get a value, say 38 here. And what did we have before here? We had 40. So if we could look at these two tables side by side, when n is 500, we're getting pretty good results. And we dropped n down to 200 and got pretty good results between the simulated and the asymptotic relative efficiency. Now, what would happen if you decided that although the missing at random labels are non-ignorable, what would happen if you went ahead and decided just to use the rule where we ignore the labels? Well, when we work out the excess error rate, where we don't ignore it over the excess, yes. So when we put the excess error rate for the, when we take the, no, it doesn't want to. When we take the excess error rate of the rule based on for the full model divided by the excess error rate for the one that ignores it, then you can see that it's got very bad efficiency. So if the labels are non-ignorable, missing at random, then we should try and do something about it and use the full likelihood. And so this what gave my co-author the idea to make it to depend on the entropy. So when he took some various data sets and plotted them, here we got some. How am I going for time? All right. When we plot these, here, in this first example here, we've got some cells from flow cytometry, and a technician, he actually clustered them into 4 groups. But the black squares, wish I could get my mouse to work. The black squares here are the ones that he couldn't classify, and they're the ones that are difficult. What a pity I can't get this to work. The black squares here, it just won't come. They're the ones that he couldn't classify.
Yeah, it's understandable. Yeah, yeah, it's okay.
And then when we take the second group again, these were clustered into 2 groups. These were some looking at the heart rates of some babies, and the blue ones were normal, and the red ones had were classified as being pathological, and the ones where they couldn't make a decision on looking at the videos of the cardiograms are the black squares again, and those black squares tend to be in regions in between that divide the two groups. And in this last one is where people had a colonoscopy, and I should say in this second data set here, they had 7 doctors to make an opinion of whether the baby was normal, pathological, or suspect. And if 6 or 7 of them agreed, they made a decision, classified them, and if they didn't, they could let it be a black one, a suspect, a label. And then in this case, 3 doctors looked at the videos of results from a colonoscopy, and if the 3 of them agreed, they got a circle here in this diagram, meaning that they were malignant, and they got a red triangle if they were normal. And the ones they couldn't make a decision were the black squares. It hasn't come out to be there. This is the one where in flow cytometry where they had 3 features, these particular features. And I wonder, yeah, I'm not too sure why this is just not working. Yeah. So, and then in these other cases, for example, in the top row there, in the first square, we fitted mixtures of skew T distributions to estimate the -2 log entropy. Now, minus log entropy, and then we fitted kernel estimates to them, and you can see that the black ones are the referred to the labeled ones, and the red one is the unlabeled. The unlabeled is the black, and the red is the labeled. And you can see that the unlabeled ones have high density is highest around. It's focused around the high entropy values, and because we're using minus log entropy there, and similarly over here we've got the posterior probability, the probability I should say of a label being missing plotted against minus log entropy. So, and I won't. This is in a paper. I'll leave that, and then so the. Well, this is just to say that we can, to fit this model now, we can use an ECM algorithm, the expectation conditional maximization algorithm. First of all, we can fix xi and then estimate theta. We can't, if we're fitting, say, mixtures of normals, we can't do that in closed form, the maximization over theta. This term, L sub PC miss, stops us. Doing it in closed form, and then having estimated theta, we update theta, and then we just got to maximize this function over xi, and it's like a binomial probability, so we can just use some generalized linear model program for that, and we've actually got a program that we call GMM-SSLM, that is Gaussian mixture model based semi-supervised learning with a missing data mechanism. And well, on the generative versus, we're using a generative model approach. There is the discriminative approach where we just work with the distribution of the labels given the features. But you do lose some information doing that, although it's probably more robust to changes in the model. And so although there is much interest in so there's still a lot of interest in the generative model. Now, I think I'm out of time, aren't I? I think. Am I out of time?
You still have
12 minutes.
15 minutes. Yeah, you still have time. That's okay.
Okay, well, let me go back. Let me go back here. I think I can't use my pointer because my mouse just doesn't seem to want to go. Well, let me say here that on the generative versus discriminative approach, discriminative techniques are widely used since they give excellent generalization performance. However, for large-scale applications such as object recognition, hand labeling of data is expensive. So there's still much interest in semi-supervised techniques based on generative models, in which the majority of the training data is unlabeled. And if we did use a discriminative approach, then we would lose we would lose this term log L sub U or theta, because we don't use that. We don't model what the density of Y is. We only model the probability of Z given Y. And so, but we can introduce unlabeled observations into this term here. We can add a penalty. We can view this log LPC miss theta xi as we can put some function like a penalty, just put like lambda times the entropy. And this is what was done in Granville and Bengio back in 2005 using entropy regularization. So the entropy term comes in here, even when you use a discriminative approach. Now, one of the most intuitive approaches to semi-supervised learning is self-learning, where an iterative method for learning with alternate steps generates pseudo-labels for the unlabeled feature observations, then trains a classifier using both the labeled and pseudo data. And as the training progresses, both the classifier and the pseudo label updated. So this is essentially, oh, there's a spelling mistake there. I didn't leave a space there between intuition and is. So basically, this is like using a hard version of the EM algorithm. Rather than assigning observations outright to a class, the EM algorithm uses fractional allocations. So this self-learning is really going on when we use the expectation maximization EML, when we use an EM algorithm or the expectation maximization algorithm. And the top is gone now, but this is a result that I derived back in 1975, like where you use self-learning, where you do what you, where you actually, I tried to look at the problem where you had a completely unclassified sample. You divided it at the anti-mode and then assigned some observations to the classes, and then updated the estimates. But I couldn't do that. So in order to make the problem tractable, I added on an infinite number of unclassified observations. So I turned it into a semi-supervised learning, although I was not interested in semi-supervised learning at the time. But anyway, the result came out, and we've got a very nice result that if these H1s and H2s are 1, then we've got the error rate based on the classified sample, and this one, there's a 1 here in the final line here, should be 0. So I only looked at that now. Anyway, this H1 and H2 are less than 1 in magnitude, and so it shows that this error rate is going up to 0. So in a way, this is something I looked at back in a few years ago now, 1975. It's one of my favorite results. And but here now, a few years later, looking at a case where looking at where we're interested in the semi-supervised, and we're making use of the information in the missing labels. So these are just some references that I've mentioned in the talk. And these are the references to our recent work on semi-supervised work, learning. And these are some references to some of the earlier papers. And well, that's it. So thank you.
Thank you.
Yeah.
You are muted, Ao.
Pitman.
Yes, you are muted.
Yeah, Sunny, you are muted. You have to open your microphone.
Sorry. Yeah, this is our great honor. I mean to have Professor McLachlan to speak here, and any of our co-chair would have a further discussion with our speaker, our Laureate.
Yes.
Oh, yes, sure.
Yes, yeah, Professor McLachlan, thanks for your nice presentation. I'm not people in statistics, but I have two simple questions. The first one is regarding you say you use the entropy concept to characterize the missing label data. So for the entropy calculation, naively saying, if I'm using a Shannon entropy, so for the missing label data set, so the classes you're using is the feature a class, is that right?
I'm not too sure.
Yeah, I think it's at the beginning of the second or the third slide. Okay.
This one.
The one before that, you have the text description about how you characterize the missing label data using the concepts of entropy.
Oh, yeah, this one here.
No, I think this before this. It's not about the mathematical expression. It's,
Okay.
I think is the third or the fourth. Yeah, yeah, here, yes. Yes, secondary, it is postulated the probability the feature data have missing the label depends solely on their entropy. So, so if that means you characterize the missing label using entropy. Now, in order to compute the entropy, you have to specify you have to sum over the classes, right? So here, are you using the feature as the summation index?
You don't have to, you sum over all the classes, so you don't. It doesn't need a you don't need a Z value for the entropy, because you sum over the probabilities. So where is it? So where am I? Oh yes. So here you're summing over the. You got I going from 1 to G. This is the entropy of a feature vector.
Oh, so the index I stands for the feature space.
I stands for the class label. I mean, I means that the it refers to the class. This is the posterior probability of Yj falling in the ith class, and then we've got the log of it.
But I thought for the missing label, you don't have the class information.
No, but we don't need it because we're summing over all classes.
Some of all classes. Oh, okay. And the second question is, when you talk about the ratio of the label to the not label, you think if there is a 50% of a label and 50% of unlabeled, then the number drops from 10 to something. Yes, just
Yeah. So I said this was 10, and I think if we made half the sample classified and half, this was missing, where things are missing at random, missing completely at random. We're not going to gain anything by modeling the missingness. We're just gaining by having unclassified observations. But if we were to double, to take half the sample to be classified and half, I think this 10 here becomes 0.5 or something like that. So when we or 55, but it's a percentage, I see. Yeah, this is 0.1 really. These are expressed as percentages. So 0.55 it would become. Or so when we divide by 0.55, we need about twice as many unclassified observations. Whereas here, we need 10 times as many.
Oh, okay, yes. Okay, yes, yes. Thanks for your response. Okay.
Yeah.
Okay. I can ask a question then. We have time.
Yeah, let's
Yeah.
thank our speaker, our Laureate again. It is really our great honor. And for the video recording, after our colleague finish the production of the video, we will send, the proof version to Professor McLachlan first, so that you can view it. And then if you are okay with the proof version, then we will send the link to our association's ordinary members so that they can view it. And also it will become public and open access to all the people. Let's thank again. Yeah.
Well, thank you very much.
Yeah.
I'm too happy to have the opportunity to present on this topic.
See you in the future.
Yeah.
Bye-bye.
Okay. Well, thank you.
Thank you.
Thank you. I will.
Yeah. Bye, everyone.
Yes.
Bye-bye.
Bye.
Bye-bye.
Bye.